be in tensile, right? And then over here, then you also know that element K, right, is going to be what? 0, right? Why 0? Because if we base on that equation that we see, I've drawn this earlier, that this is our normal stress, right? Right. This is our normal stress, and this is our Y, and this is how our distribution will look like. So over here is where element H is. Over here is where element what? Element K is. That's why element K is on the neutral axis. That's why the stresses is equal to 0. Okay. Any questions so far? Are we clear, right? Are you guys still having this lagging thing on your side, or is getting better?
Yeah.
Still lagging?
Yep. But if I refresh, it helps.
Oh, yeah, okay. Right. So from here, we have Px will be, so now we are done with this 150 as a moment. Then as an axial load, Px is going to generate a tensile, okay, plus by 150 pounds. Okay. And then this 150 pounds for element H and element K. So element H will be in the tensile also. So likewise, element K will also be what? Tensile. So when that's the case, the formula we're going to apply is stress X is equal to Px divided by what? Divided by area. So this is where we call it under what? Axial what? Loading. Okay. Right. So far so good. We are clear? Or no comment? Okay, I'm going to assume that we are clear. Okay. Anyone, anything to clarify for now?
Yeah. How did you know?
We don't have the reaction forces there.
Say it again.
Is there a reason we're not considering the reaction forces?
We are not considering the reaction forces because we are analyzing how the structure will deform, not the reaction at the not the reaction at the what do you call at the at the fixed point. We are not calculating the reaction over here. Yes.
How did you know that the neutral axis was there? Did it say in the question?
So the neutral axis is over there because the location of element H and element K.
Right. Okay. Thanks.
Okay. That's a very good question. How do you know? If not, you can make a guess. Okay. Because whatever we're going to calculate is on element H and element what? K. Are we clear?
Yep.
Okay. Thank you. Right. So one view down. Okay. So we're going to look at a different view now. Okay. We are going to look at a view where we have, I'm going to draw a different view. Okay. I'm still going to copy this so you all can see clearer. Again, this is not a trivial problem because most of the time when you see this, a lot of not just yourself, engineers get really afraid because it's compound loading or combined loading. Once you break things down, it's very, very clear. I repeat again, once you break things down, things are so much easier. Okay, so the next thing we're going to do, we're going to look at a different view now. Okay, we're going to view from the plan view now. So this is my X. Okay, this is my Z. And this is my rotation in my Y direction. So we are looking this thing from the plan view now. Okay, so we have one end that's fixed. Then we're going to have our beam. All right. So this is our beam. So we are looking at the plan view. So we have a, I mean, the drawing is not perfect. So we have a circle down here, right? Then again, find the location of the neutral axis. Okay, so this is our neutral axis. Right. Then the next thing you do, as the same procedure as before, locate your element. So now, wait. So now, this is your element H, right? And then over here, this is your element K, right? And then you put in all your forces. So you have over here, you have 150 pounds. Now, this 150 pounds, we already analyzed already, okay? So if that's the case, you just put a tick. You already analyzed already. You don't need to analyze anymore. You don't need to double it up, okay? Then you have a 200 pounds over here, right? And then over here, you have 50 pounds. And then somewhere over here, you have 150 pounds. Okay, somewhere over there, you're going to have your. So next, we're going to calculate what's going to happen at element K. Now, element K and H will have moments. Okay, will have moment acting on this structure now. Okay, I repeat again. Element H and element K will have moment, right? Now, the difficulty comes here again, okay? So I'm going to write down here, when is it a moment? Right? And when is it a torque? Right? So we know, right? We know that moment is equal to force multiplied by perpendicular distance. We know that. Whereas the torque is equal to force times radius. You see the difference, right? Once is a perpendicular distance, once is a radius. Some of you will say, yeah, Eugene, the radius is also the perpendicular distance. Am I right? Yeah, absolutely right. You're not wrong at all. You're absolutely right. The radius is also a what? Perpendicular distance. Now, question for you guys. All these forces over here that you see now, based on this view, is it a moment or a torque? Anyone? Based on this view now.
They're all three of them are moments.
And why is it a moment? You're right.
Because we're not dealing with the radius at this time.
Okay, you're right. You're not because of the radius. But if we draw the deformation, okay, I don't know how is it going to deform. I'm just going to guess. Okay, I'm just going to guess. If we were to draw the moment, okay, if the structure deformed this way, right, under all these forces, right, the structure will deform. How did I draw the deformation earlier? I used red. So if I'm going to guess, okay, the deformation induced by all this moment, I will deform this way. This is just a guess, right? So it's still what? It's still under bending. Yes or no? Why is it still under bending? The deformation, I call this still under bending. Right? This is still under bending moment because the deformation is either a smiling face or a what? Or a sad face. Yes or no? You look at how the neutral axis deform. Is it a smiling face or what? A sad face. So when that's the case, it's going to be a moment. So the moment will be about y. So now I'm going to call clockwise positive. I'm not doing static analysis, okay? So I mentioned about moment, right? About y. Again, I'm not doing static analysis. I'm just calling what? Anything that is clockwise is positive. So this is not static analysis. Static analysis is what? In static analysis, what do you observe? When you write out static analysis, right? You will say summation about moment in the y direction at a certain point, or just at a certain point alpha is equal to what? 0. This is static analysis. What I'm doing now is not static analysis. I'm just summing all the what? I'm just summing all the moment. Are we clear? Okay. So when that's the case, the 150 will be minus 150 multiplied by a distance 4. Sorry, plus. What do you mean by minus? Right, because I'm assuming anything that is clockwise is minus. Sorry. Minus by 150 multiplied by 4. Because this 150 will generate anti-clockwise, right? And I say clockwise is positive. And then minus 50 multiplied by 10. And then plus by 200 multiplied by 10. So this will be equal to minus 150 times 4 minus 50 times 10 plus by 200 times 10. So it's positive 900 Newton meter, and it's going in a clockwise direction. Okay. So again, at this point, you will say that element H, right? Element H, the stress will be equal to what? 0. Because it's on the what? It's on the neutral axis. Then element K is going to be compressive. Okay. Why are we doing this? Because we are breaking down each force, each moment, each torque, okay, and how they are behaving on the what? Element. Because later on we have to combine all of them together. And if you don't get it right, okay, the mistake will be very easily made. Okay. And then the next one, so all these forces will contribute to a shear force. So the shear force, all the shear force going in that direction, okay, in the Z direction. Okay, so and anything that is going upwards is positive in my shear force. So you have 150 plus by 50 minus by 200. So this is going to be 0 Newton or 0 pounds. Sorry, everything is in pound inch. What am I doing in Newton meter? Do apologize. Okay, so everything is in pound inch. Okay. So we have done 2 views already. Anything else to analyze? No. So we know that for this case, right, because it's 0, we happen to be lucky for 0. So for this case, we know that the shear will be equal to VQ over IT. But for this case, the shear due to VZ is equal to what? Is equal to 0. Okay. Then the last one, we have to look at our last view. So the last view over here will be on Y, Z. This is rotation about X. Okay, so when we view this, it's going to look like this. Okay, I'm going to draw it wider a bit. All right. So this is our beam. This is our circle. Okay. And this is the position of our neutral axis. Right now, the neutral axis is a dot. Right? So this is the position of our neutral axis. And then we're going to put in all our loads. Okay, we're going to put in all our load. So we're going to put in, so we have